Okay, so I think we can get started now. So thank you everyone for coming today to our multi-institutional AGN seminar series. And today it's my pleasure to introduce Misty Bentz. Misty got her PhD from Ohio State University, and she then was a postdoc and Hubble Fellow at UC Irvine, after which she joined Georgia State University, where she is now a full professor in the Department of Physics and Astronomy. And Misty has received numerous awards. Was really impressed. In addition to her Hubble Fellowship, she recently got the UCSD Margaret Burbidge Visiting Professorship in Physics and Astronomy. And I noticed she also got the Career Award, and she has numerous awards as PI from NASA and NSF. And I noticed that she has an impressive array of observing proposals that she got as PI from very competitive ground and space-based observatories, including most recently the extremely competitive JWST ERS proposal on which she is PI. And we hope to hear about that exciting project today. And I noticed that all of this she somehow managed to do on top of receiving these numerous outstanding faculty awards and teaching awards, just showing that she's really an impressive teacher and mentor and faculty colleague. And I wanted to say that I think that Misty's done a really high impact work for the AGN science community. Anyone doing anything related to black hole masses uses her work. I think actually Gabby mentioned this, that at the time that she published the LAMP papers, she essentially doubled the number of objects with reverberation mapping masses known. I think she's done a tremendous job advancing this field, and she wrote this amazing review article recently that I highly recommend, and it's a very useful resource for your students as well. And I can see that she's now branched out into a diverse array of research projects relating to AGNs and their host galaxies, among other things. And I should say that speaking of diverse interests, I noticed looking at her website that she also composed a 3-piece musical piece in 4 movements from scientific data. So I didn't know about this, Misty, but that's very intriguing. And as a member of the Orange County Flute Ensemble, she co-organized and performed a multimedia concert at UC Irvine. And this performance, I guess, was called Fantasy on AGNs. So I find that really intriguing, and it really speaks to her incredible creativity and diversity of interests. So someday, Misty, you have to tell me about all of that. So it is my pleasure to introduce Misty to you today, and she will be talking about a wide array of topics involving black hole measurements in AGNs. So I will let you take it away, Misty.
Thank you so much. I don't know how to follow an introduction like that, and so I will just say thank you, and I will go ahead and get started. So I'm going to be telling you today about a lot of different kinds of projects that I've been focusing on over sort of the last 10 years. And hopefully I've kept this relatively short and relatively simple and to the point, and so we will see how it goes. This is a little bit of a new talk for me. So I'm going to start out with something that I don't think needs a lot of introduction, because we've already had so many wonderful talks on this topic throughout this seminar series this summer, which I am very thankful has been put together, and I've been attending as many of the talks as I can and listening with a lot of interest. So thank you everybody who's already presented, because I think you have all made the point quite well that black holes affect the galaxies that they live in. And in some cases, black holes affect the environments beyond their host galaxies as well, as you can see in 2 of these images that really show dramatic feedback effects from the central supermassive black holes in a galaxy on the left and in a galaxy cluster on the right. And you can see these powerful jets of material that are shooting out of the center, sometimes aligned with the galaxy, sometimes misaligned, and impacting the gas in the galaxy and in the circumgalactic medium, or even the intercluster medium as well. So we know that black holes are important. Not only do we see the effects of their feedback in observations, but we also see their effects in simulations where we just don't get galaxies that look like what we observe in the universe unless we have black hole feedback included as part of the evolution of the galaxy throughout the simulation. So black holes are important. I think we can all agree on that. That's why we study AGNs. I don't need to convince anybody here of that. So an important point in all of this, though, is that the amount of feedback you can get from a black hole and the amount of influence it can have on its galaxy and its environment are directly related to its mass. And so the mass is a key parameter here. And for those of you students, especially who may not be super familiar with how we measure black hole masses, I mean, it's an invisible object. You can't see it unless it's lighting up some gas around it. How do you measure the mass of an invisible object millions of light years away? Well, you have to use some sort of test particle that's luminous that you can actually see in your observations so that you can trace out the velocity of that test particle and the position of the test particle. So basically, you're using a very simple gravitational law and using a luminous tracer particle to tell you about the gravitational field of the black hole. And from that, you can determine what its mass is. And this is most easily seen with the black hole in the center of our own galaxy, Sagittarius A star, where a heroic effort in monitoring the center of our galaxy with adaptive optics has traced out the positions of numerous stars. And in particular, you can see the star that's tracing out the yellow curve that will complete itself here. And those stars, we can actually see individual stars moving around. We can determine what their velocities are and the size of the orbit. And from that, we can constrain the mass of the thing they're orbiting around to be about 4 × 10⁶ solar masses. So this is sort of the easiest way to picture how we measure a supermassive black hole mass, but this technique only works in our own galaxy because we have to be close enough that we can see individual stars. We're only about 8 kiloparsecs from the center of our galaxy, but other galaxies are millions of parsecs away. And so we can't see individual stars in them. So we need a different kind of technique for measuring black hole masses in other galaxies. But the basic principle will be the same. So another kind of test particle that you can use are water masers. So these are molecular clouds aligned in a disk in the center of a galaxy that end up mazing and letting off light at specific wavelengths. And if you're very lucky that you actually have this geometric arrangement with gas conditions that allow these clouds to maze, and if you're lucky enough to have the galaxy inclined to your line of sight just so, you might be able to trace out the positions of these clouds and their velocities so that you get this very nice Keplerian rotation curve that you see on the left, where you see the red shifts and the blue shifts from the different sides of the disk very clearly. And so that's another way that you can constrain the mass of a black hole. In general, though, we don't have just the right conditions and just the right inclination to see water masers in very many galaxies. And so other techniques involve using more common stars and gas. And again, in these cases, you're looking at different positions within the center of the galaxy. So you're spatially resolving different positions and you're looking at the bulk flow of the gas or the bulk motions of an unresolved population of stars. So this is a whole bunch of stars contributing light together in 1 pixel. And then you're looking at how that changes from pixel to pixel across the center of your field. And so you're either looking for how the gas velocity is changing as a function of position, or you're looking at perhaps how the stellar velocity dispersion is changing as a function of position as well. And these can also be modeled and provide black hole masses as well. But you'll notice in all 3 of these examples here, first of all, the water masers, you have to have everything just right and everything inclined just right and really limited in number, so you can't get a huge number of masses this way. And all of these techniques are limited by spatial resolution. You have to actually be able to discriminate between the velocities at different locations in the center of a galaxy, and you need to peer deep enough that you're actually determining the gravitational influence of the black hole and not the rest of the surrounding galaxy. So that's a problem, but also the black hole mass that you get in the end depends on the distance, because you have to change your angular size measurements on the sky to a physical size measurement. So not only do these galaxies have to be close enough that you have enough spatial resolution, but also you need to know the distance quite well, so because it goes directly into the accuracy of the black hole mass that you get out in the end. So there's another technique that we use that doesn't rely on spatial resolution at all. Instead, it relies on time resolution. And so we can actually use, excuse me, time delays in the centers of active galactic nuclei to measure size scales. And so this is my very simple cartoon for how that works. On the right, we have a black hole with a very simplistic broadline region as arranged as a ring around it with a specific radius. And if you, for example, have a delta function outburst from the accretion disk around the black hole, that light will travel outwards, it will photoionize the gas in the broadline region, the gas will recombine and emit photons. Some of those photons will travel to your telescope on the left side, obviously not to scale. And you'll see that all of the photons don't arrive at your telescope at the same time. There are time delays caused by the extra path length that some of these photons have to travel. So photons that are emitted from the close side of the ring arrive with no apparent time delay compared to that delta function outburst that you saw. But photons that arrive from the back side of the disk arrive with a time delay that's 2 times the radius divided by the speed of light. So if you look for just the average time delay of the response of the broadline region to some variation in the continuum emission, that average time delay gives you the radius, the average radius of the broadline region divided by the speed of light. We know what the speed of light is, and so just by working in time space instead of spatial space, we can actually determine physical sizes on the sky. So what does this look like in data? On the left is an example from my dissertation, like time ago. It's just a nice clear light curve where you see continuum emission on the top and a broad emission line flux on the bottom. You can see that there's this nice spike in the continuum emission and then it levels off. And you see that pattern repeated in the broad emission line, in this case, H beta in the middle of the optical region. And you see that it also has a nice spike. It's somewhat blurred out because, again, you're getting different response times from different parts in the broadline region. And you see there's an average shift or delay of the response of the broadline relative to the continuum. So in this case, that average delay is about 6 light days, 6 days. And so that tells you that the size average, typical average size of the H beta emitting broadline region at this time in this galaxy was about 6 light days in size. So that's one piece of what we need to get the black hole mass, is the characteristic size of the orbits of the tracer particles that we're using, in this case, the broadline region gas. But we also need to know the velocity. Well, in a broad emission line quasar or broad emission line Seyfert, right, that emission line is broadened because of Doppler velocity, so blue shifts and red shifts. And so if we just measure the width of the emission line, that gives us a handle on the characteristic velocities of the gas in the broadline region. And so we can put those together and get something that looks like a black hole mass modulo this F scaling factor out front. So F is where all the messy details reside. It depends on the geometry and kinematics of the gas and the inclination to our line of sight. And in general, I'll come back to this later, but in general, what has mostly been done is to treat that as just a typical scale factor, assume that the average value is kind of similar from object to object, and just determine if we think that all black holes are basically the same and they're drawn, you know, the reverberation sample is basically drawn from the same sample as other galaxies with black hole mass measurements. What scale factor is needed to bring all the reverberation masses into agreement with other black hole masses that have been measured? And so when you do that exercise, you find that F is about 5. Give or take, it depends on exactly your methods and your sample. But most of the numbers come out to be between about 4 and 6. So that is typically how we get reverberation masses. And like I said, we're going to come back to this again in the future because there's more to this story, so stay tuned. If you're in the market for a new review article on reverberation mapping that covers not just the broadline region, but reverberation mapping from X-rays all the way through the infrared, we do have a new article out that Shabita was kind enough to mention. And so you can look for that in iScience, which is a new journal I had not heard of, but they wanted us to write a review, and so we did. Okay. So what this means with all these different black hole mass techniques that we have is that in the local universe, we have quiescent galaxies being preferred for the black hole mass measurements. You're typically using stellar or gas dynamics in the center of the galaxy, a nearby galaxy, quite often an early type galaxy. And then dynamical modeling of the kinematic measurements as a function of position in order to constrain the black hole mass. And so you get something like the M sigma relationship, which I think most of you are probably familiar with. Almost all of these points on the M sigma relationship are from quiescent galaxies. You see that there are a lot of red points. Those are all early type galaxies. It's fairly simple to model an early type galaxy as a ball of non-collisional stars. And so that's why early type galaxies seem to be preferred for these types of studies. But if we want to talk about black hole masses at any sort of cosmological distance where we don't have the spatial resolution needed to apply those techniques, then you have to use AGNs. That's where we can actually find black holes that are far enough away from us, as if we look for the ones that are lit up. And so estimating their masses depends on using the results from reverberation mapping. One of those is the radius luminosity relationship. So if you look at the average size of the broadline region, it scales along with the luminosity of the AGN. A brighter AGN is going to more highly ionize the gas around it. And so you'll find just the right conditions for the emission of a specific line at a larger distance. And then if that luminosity in the center is to turn down, a lot of that gas will recombine, and the perfect conditions for that emission line will now appear closer. And so you see this breathing effect in AGNs, whereas they get brighter, the broadline region scale size moves out. As they get fainter, it moves in. And it's not that the gas is moving out in and out, it's a photoionization effect based on that central illumination from the AGN. And so you can take this radius luminosity relationship that's calibrated here, and instead of spending night after night after night at the telescope getting spectra to measure a time delay in an AGN, you can just measure its luminosity from one spectrum, read off what the size of the broadline region must be, and then combine it with the width of the broad emission line to give you a black hole mass estimate. And so that's where the vast majority of black hole mass measurements at cosmological distances in the literature come from. So like all the black hole masses for the Sloan Digital Sky Survey Quasar Catalog basically use this kind of technique. But that means we have two different scales. We have one black hole mass scale that we use locally and a completely different black hole mass scale that we use at higher redshift. And so if we want to try to observationally constrain the evolution of galaxies and black holes across the observable universe, we're sort of just assuming these two things are the same. They use completely different techniques, completely different kinds of data. They're going to have completely different underlying biases in them. And we all have just sort of swept that under the rug until now.
Misty, can I ask a question?
Sure.
This is Claire Max. So this lambda, L lambda at 5100, is that indicative of the AGN activity, or is that a general luminosity?
That's the luminosity of the AGN specifically. So this particular plot that I'm showing you has, it came out of a lot of the work from my dissertation as well, in which we had to very carefully determine the starlight contribution to any sort of spectroscopic luminosity that we measured at 5100 angstroms, and very carefully subtract the starlight contribution so that we were isolating just the AGN luminosity at that wavelength.
Because I'm sitting here trying to understand we think that AGNs are episodic as gas falls in and then doesn't fall in and so forth. So what if you have an AGN that used to be brighter than it is now, and so lambda L lambda is low relative to the broad light region size, or I don't know, how does that go? If you know, the benefit of some of the dynamical mass measurements for nearby galaxies is you don't even have to have an AGN; it can just be a black hole. So how does the episodic nature of AGNs affect the right-hand plot?
In general, these are all, first of all, broadline AGN, which means they're fairly strong AGN. So it's there's a lot of gas there that's accreting onto the black hole, which is allowing it to release all of that luminosity. And so in these cases, you know, if there's no gas there, there will be no broadline region. So we won't detect it as a broadline AGN, and we can't use this technique. It won't appear on this plot. If it's already a strong AGN with a lot of gas around it, then if it flickers up and down in luminosity, it just means that it's going to slide up and down this particular plot. But the width of the broad line is going to track with it as well. So as the luminosity goes down and as that radius that you're probing comes in, you're probing gas that's moving faster because it's closer to the black hole.
Okay.
And so when you calculate the mass, you're going to get basically the same value as for that AGN as you would in a higher state where you're tracking gas that's further out. It's going to be moving slower. And we actually see this in AGNs where we've done this experiment multiple times. As luminosity flickers up and down, the size of the width of the broad emission line tracks with that change in luminosity, that change in time delay. Yeah.
Thank you.
Sure. Okay, so we have two different black hole mass scales, one for nearby, one for far away. We should check those. And you know, doing black hole mass comparisons is actually really hard. There are not that many in the literature for all of these different techniques that I've talked about. But one that was actually fairly highly publicized is the case of Hawaii. I think I'm saying that right, in M87, the EHT image. So this black hole in M87 is at a distance of about 17 megaparsecs, so it's fairly nearby. It had previously been studied with gas dynamics and stellar dynamics before the EHT project. And what you see on the right-hand side is a plot of black hole mass on the y-axis, and then you see two horizontal sort of gray regions in that plot. One of those is labeled gas. That's the range of masses that were expected based on gas dynamical modeling in the center of M87. And above it, you see a completely separated bar, gray bar range. That's the mass range expected from stellar dynamical modeling in the center of the same galaxy. It's the same black hole. It should have the same mass no matter what technique we apply. And in this case, you can see that they didn't agree and they don't overlap at all. And so when the black hole mass was actually constrained from the EHT observations, and they did that in 3 different ways, which you're seeing as 3 different colored bars here, you see that all 3 different ways agree with each other, but they also only agree with the stellar dynamical modeling result. In which case that's telling us that there's something perhaps biasing the gas dynamical measurement in this particular case. And so that is a little bit of a concern, because if you use one technique over another, you would hope that it would give you the same black hole mass as any other technique, but that may not always be the case. And it's something that we should check. And so if we want to be able to compare our higher redshift mass ladder to our local universe mass ladder, the only way we can do that is by comparing some dynamical modeling measurements. In this case, we've chosen to focus on stellar dynamics with reverberation mapping. And this is really hard. So I have a Venn diagram here. I almost never get to use Venn diagrams anymore, but they're fun. So here's one for you. So in the case of stellar dynamics, in general, as I sort of mentioned earlier, most of the galaxies that have been studied are early type. These tend to be quiescent galaxies. So if you just have a mostly quiet, gasless, dustless ball of stars, it's actually a fairly uncomplicated modeling process as far as modeling goes. There's not a lot of extra complications that are thrown in. In order to do this, you need really high signal to noise spatially resolved spectroscopy. And in this case, you're looking for absorption lines. So you're looking for faint signatures on top of faint signatures. It's distance limited in that the galaxies can't be too far away to use this technique, but also the mass that you get depends on the distance that you assume. And in some cases, it's called the gold standard of black hole masses, which I think we can agree with in the case of a relatively gas-free and dust-free ball of stars. But if you start talking about later type galaxies, it gets a little more complicated. And so that's why that question mark is there. On the other hand, we have reverberation mapping, which can only be applied to broadline AGNs. It requires a completely different set of data. So in this case, it's high cadence and high signal to noise spectrophotometry of emission lines. It is distance independent in that you are not relying on spatial resolution, and you can, in principle, apply this technique at like redshift 4. You just have to wait a long time because the time delays get stretched. But we have this F factor uncertainty that I told you about earlier, which is a bit of a limitation. And in general, these two techniques, it's not easy to apply them to the same galaxies. There's a very small region of overlap where you can do both of these. And that is for the case of very nearby. So we're talking about redshift less than 0.01. So distance is less than about, I don't know, 50, 60 megaparsecs. And they have to be Seyfert ones. So Seyfert ones are rare in the very nearby universe. And so that means this is only going to be a small number of galaxies that we can ever apply these two techniques to. But it's important to do that because we don't know for sure at this point if all black hole masses are on the same scale. Are we comparing apples to apples? So when we tell our modeling friends that we have constraints on black hole masses and galaxy properties at redshift 0.3 and 0.5 and 1, as well as local universe constraints, and they put those into their models to tell us about how galaxies and black holes are forming and evolving with time, if those scales are off, then it's going to affect the results that we get in the end. Okay, so I told you a small number of galaxies would be available in order to do these tests, and until recently it's been a whole two galaxies, NGC 4151 and NGC 3227, with the references there if you want to go look them up. So this plot is really boring because there's not a whole lot going on, but I'll orient you here on the bottom. We have the reverberation-based black hole mass, and on the y-axis, we have a dynamical black hole mass, and then I've color coded. In both cases, there's stellar and gas dynamical mass measurements, and then also a reverberation-based mass measurement for those two galaxies. And so you can see how those agree or don't agree with each other, with the dotted line showing you the line of unity to help you with that. So at least in the case of NGC 4151, things look kind of okay. But in the case of NGC 3227, both dynamical methods are giving significantly higher black hole mass measurements than has been measured with reverberation mapping. And then down at the bottom, I have NGC 4395 there, which is a little tiny dwarf Seyfert galaxy at 4 megaparsecs from us. It doesn't even have a bulge, but it has a nuclear star cluster. Currently, we cannot measure the black hole mass with stellar dynamics in 4395 because the stellar velocity dispersion is so low that it's comparable to the instrumental resolution of what we can measure. So what you'll see, though, is that the reverberation mass and the gas dynamical modeling mass sort of agree, although that's helped by the really large error bars on the gas dynamical modeling. So in this case, we sort of don't know what we have. In the case of one AGN, it sort of looks like things agree okay. In the case of another one, we might get a little bit nervous. And so clearly 2 is not enough. And so we have undertaken a project to add several more AGN to this plot, and really do the best that we can with the few galaxies that are available to see if we're really comparing apples to apples with these black hole mass measurements. I am not a modeling expert, and so Monica Valuri and Eugene Vasilev are our 2 modelers on the team, and they know all of the details related to the modeling and all of the potential pitfalls that go along with it. Chris Onken is helping as well. He's at Australian National University. He's another reverberation mapping expert. And so we've tried to devise a team of data and observational experts along with modeling experts so we can really try to do the best that we can. And we've got 4 more objects that we are at various stages of completion with. And so what you see on this plot, those black bars are showing you the reverberation masses that we have for those 4 additional objects, and we're in the process of acquiring dynamical mass measurements right now. So I'm going to sort of walk you through our progress on these different objects so you can see how things are going along. So NGC 6814, which you can see in this gorgeous, almost face-on spiral galaxy. One of the graduate students in my group, Katie Merrill, is working on Gemini NIFS IFU observations of the very center of this particular galaxy. And she has re-reduced the data, she has pulled out kinematic measurements, and she actually has stellar dynamical models running right now that are going to very shortly constrain the black hole mass of this particular galaxy through dynamical modeling. And our reverberation mass for this object is about 1 × 10⁷ solar masses. And so that's assuming a specific F factor, but we're hoping that we'll end up with something, that will tell us how good that reverberation mass is. We do have a new distance measurement to this galaxy because it's very important for the dynamical modeling. And that was a measurement with HST observations and finding Cepheids in the galaxy. And so when you take the multicolor imaging that you need for a Cepheid project, you can make really pretty pictures like the one that you see here on this slide. So NGC 6814, we're actually hoping to have results for that by the end of the summer, and then Katie will be writing up the paper on that, which if all goes well, hopefully we'll be submitting before the end of the calendar year. So we're actually getting pretty close on this particular object. But Katie's also working on a second object. In this case, it's a very different kind of morphology for the galaxy. It's an S0 galaxy, which should give us an interesting new set of kinematics to model. She has the kinematics almost ready to start modeling, but is doing the final checks on that now. And so you can see the maps for the kinematic measurements. And I should have walked you through that on the last slide, but I'll do that here. And so what you see are 6 different panels. On the left is the velocity in kilometers per second. You see redshift and blue shift as you move across the middle of the galaxy. The next one to the right is the velocity dispersion, sigma. And you can see that the velocity shift is actually quite a bit larger than it was in NGC 6814 because this is not a face-on galaxy like that one was. The velocity dispersion is a bit higher in this galaxy as well. And then you see the higher order moments of the shape of the emission line. So H3 is a skewness parameter and H4 is a slightly different parameter. And then H5 and H6 as you go up. And so these will help constrain the dynamical models and tell us how the stars are moving in as unresolved bulk properties as you move from position to position within the center of the galaxy. So this galaxy is not far behind on prep work. We're hoping that we can have this one done shortly after we finish up the results for NGC 6814, the previous one. And so these 2 galaxies are making up Katie's dissertation, and she'll have 2 completely different morphologies of galaxies to talk about and to tell us about how well the dynamical modeling compares with the reverberation masses. The next one is one that those of you who are X-ray enthusiasts might recognize, MCG-63015. This is an object where we were able to measure a reverberation mass just recently, actually. It's a very small black hole, 2 × 10⁶ solar masses. And you can see my research assistant here, Major Scotch, has been sort of helping me do the data reduction for this particular object. So I've been spending the summer getting familiar with data reduction in preparation for VLT Symphony observations, which we acquired, I believe, just before the pandemic, actually. So pandemic has sort of slowed this project down a bit, but we're getting close to being done with the data reduction, and then we will make the kinematic measurements to determine how the velocity dispersion, and higher order moments change as a function of position in the center of this galaxy. And again, you can see the morphology of this object is quite a bit different from the last 2 that we were looking at. This is a closer to edge-on spiral galaxy with a dust disk in the center. And so again, it will be really interesting to see how the different characteristics of the galaxy may or may not make the stellar dynamical modeling easy or hard, and how those results end up comparing with the reverberation mapping. And NGC 3783, another possibly favorite of this group, whether or not you study X-rays or any other wavelength in AGNs. This is one of the brightest Seyferts in the southern sky. We have VLT Muse observations, and this is in collaboration with Sandra Raimundo and Mariana Vestergaard at the University of Copenhagen. So they are the ones who are in charge of getting the data prepared for stellar dynamical modeling in this case. But we have the Muse observations in hand, and I believe they are working with a student to get those observations reduced and then to get the kinematic measurements made. And in this case, we'll be looking at, again, a slightly larger mass black hole, somewhere in the range of 2 × 10⁷ solar masses. Now, that's where we are with the stellar dynamical modeling at the moment. We have a lot of data in hand, and we're making very good progress on it and hoping for a lot of fun and interesting results in the next 1 to 2 years, which is great. But there's the other half of this, which is the reverberation mapping. And in particular, I have been recently spending a lot of time focusing on reverberation mapping of NGC 3783. We had a new paper out earlier this year where we did a completely new reverberation campaign on this object. In this case, nobody had to sit at the telescope. It was a robotically controlled telescope that got us the spectra, and then other smaller robotically controlled telescopes that got us all of the photometry as well, so that we could track out a very well sampled continuum light curve and then the broad H beta emission line light curve as well. And so with that new campaign, we were able to put tighter constraints on the reverberation mass for NGC 3783. And we didn't realize it at the time, but the gravity team working with VLT was also looking at NGC 3783 around the same time. And we heard about that in the very first talk of this seminar series, where the gravity observations were able to constrain a black hole mass in 3783 around the same time as we were. And our mass agrees with theirs quite well in this particular case. But wait, there's more. We're not done with NGC 3783 yet, because I have to come back to that F factor, right? That annoying scale factor at the front of most reverberation masses. Well, we don't actually really like that scale factor. It's sort of been a convenient way to deal with something that's really complicated for a while, but it's not optimal. And in fact, it's not making full use of all of the information available in reverberation mapping data. So in fact, we can do better. We can actually map out, that's why it's called reverberation mapping, but we can map out the position of gas and velocity of gas in the broadline region using a more complicated assessment of the reverberation mapping data that we're getting. So this is a complicated slide, but I'm going to walk you through it to make it easy. So first of all, you, the observer, are sitting at the bottom of the slide, looking up towards the top of the slide. Okay, and along the top here, I have 3 different broadline regions. They have the same geometry, so it's a ring inclined at some angle, but they have 3 different sets of kinematics. So the one on the left is rotating, the one in the middle has gas that's just infalling towards the center, and the one on the right has gas that's outflowing away from the AGN. And so then I have arrows that are color coded as to whether or not you'll see a red shift or a blue shift from that part of the ring. So for the rotating ring, for example, the left-hand side is coming towards you, and so that would give you a blue shift. And the right-hand side is moving away from you, so that would give you a red shift. Those 2 sides are going to have a moderate time delay. They'll have a time delay that's about the width of the broadline region, because the gas that's on those edges has to travel an extra path length compared to the front of the disk to get to you. The gas at the back is going to have the longest time delay, and the gas at the front will have 0 time delay, and you'll get a long set of different path lengths that those the photons from the back and the front are going to have to travel. So if you look at the time delay versus the velocity in the emission lines, basically take your emission line, split it up in velocity bins, look at the time delay as a function of velocity in the emission line, what you'll see for a rotating disk is something like the bottom left panel. You'll see a symmetric response with longer time delays in the center, shorter time delays on the wings, and you'll actually see a spread of time delays near the line center. So the average will be kind of longer, but you'll see long time delays and very short time delays from the back and the front of the ring. In fall, you're going to have blue shifted gas on the very back. So you'll have long time delays associated with the blue shifted gas because that's the back of the disk falling towards you. And the front of the disk, which has no time delay or short time delays, is moving away from you. And so that will be red shifted gas. And so you'll get an asymmetric response in the velocity time delay region down below. So you'll see long time delays on the blue shifted side, short time delays on the red shifted side. Outflowing gas has a similar pattern, but it's the opposite. So you have your long time delays associated with your red shifted gas and your short time delays associated with your blue shifted gas. So you can actually map out how the gas is arranged in the broadline region by using all of the information that's encoded in reverberation mapping data. So instead of just taking the emission line and squishing it down into one flux measurement, now you're looking at the range of time delays as a function of velocity. And there's a couple different ways you can do that. And the way that we recently did that for NGC 38783 is to use a modeling code called Caramel, which starts with the assumption that the broadline region can be approximated by a whole bunch of individual little clouds. And then it looks at different possible combinations of geometry and kinematics for those cloud particles to tell you what sets of models match your observations, and therefore what sorts of properties can you constrain for your broadline region. And so we actually did this. I just got the referee report on this paper earlier this week, and so it will be coming soon to an archive near you. But we were able to constrain the broadline region geometry and the black hole mass with no F factor needed. So if we know all the details of the broadline region, we know where our test particles are, we know how far away they are from the black hole and how fast they're moving, we can constrain a direct black hole mass with no F factor needed. And we were able to do that in this particular case with a broadline region that is well represented by a thick disk that's inclined at about 20 degrees to our line of sight. And with the black hole mass constrained, not just by the broad H beta emission line, but also the higher ionization helium-2 emission line that's near it. We have a joint constraint on the black hole mass of about 3 times 10 to the 7 solar masses. And again, this is with no F factor. So this is much easier to compare to what we get from the dynamical modeling that will be coming from our MUSE observations soon. So this paper will be coming out soon, so maybe keep an eye out for it if you're interested in hearing more about the details. But we have to sort of come back around because we can apply that technique to some of the other AGNs in our sample as well, including the first 2 that were on that plot that I showed you, NGC 4151 and NGC 3227. And so this is work that one of my graduate students, Justin Robinson, is doing, is to take the reverberation data that we already have in hand for these 2 particular AGNs. You can see the light curves for the continuum and H beta down below each one. And do the full modeling of the full reverberation response encoded in the broad H beta emission line for these 2 objects and determine their black hole masses without needing to rely on an F factor. And that will help us do a better job of comparing the dynamical masses that exist already for these galaxies with the reverberation masses and not having to wonder how much having an F factor in front might be skewing our results. And so that work is currently underway. In fact, his models are running on computers right now. This process takes a little while. It takes about 3 weeks to a month to run these models. But the results shall be quite interesting, I am sure, and those should be done and ready for us to look at in just a couple weeks here. So stay tuned on that one as well. So NGC 4151 is a fun galaxy. I'm sure some of you have probably studied it at various times as well. We actually just redid the stellar dynamical modeling measurement for this particular galaxy, because when we were looking at the original mass that was published, we noticed that there were several ways that we could improve the treatment of the data, as well as improve the assumptions going into the modeling to try to get a better constraint, or at least a more reliable constraint on the black hole mass. And so this is work that my former PhD student, now Dr. Caroline Roberts, completed. And in fact, the paper appeared on in AppJ today. It's been on AstroPH for a couple months, but just appeared today in the journal. And so we did from scratch, pulled down the data from the archive, re-reduced it, improved the reduction pipeline as much as we could at every step along the way, remeasured the kinematics and improved that process in several ways as well, and then modeled with a new code that we also paid very close attention to all of the possible model constraints that were going into the assumptions here. And constrained the black hole mass to 1.6 times 10 to the 7 with a fairly large uncertainty on it. And so that's perhaps a little bit disappointing because it's not a super strong constraint, but it really, I think in the end, we decided that that was probably about the best that we could say with this particular data set. And there's a reason for that, and that leads into my JWST proposal that I led. So JWST, I believe, is supposed to launch in November or December of this year. We've all been waiting. Fingers crossed that there are no more delays, but also if they need another delay in order to make sure everything's okay, then that's fine with me as well. And so one of the problems of trying to do stellar dynamical modeling in AGN is that the AGN in the center is really bright. And you're looking for faint stellar absorption features as close to that central AGN as you can get. So when you do that from the ground, we've been doing that with adaptive optics, which does a good job of, helping constrain most of the light, or at least a large fraction of the light in the AGN into a diffraction limited spike in the center. However, with adaptive optics, there's always the uncorrected light that is there as a seeing halo around your diffraction limited core. And so what that means is that for a really bright AGN like NGC 4151, you have a lot of excess noise from that AGN point spread function that's uncorrected, that's sort of swamping the signatures that you might hope to measure from stars in the galaxy around the AGN at very close angular distances. So the thought was that, maybe if we go to space, if we're not looking through the atmosphere, if we don't have to deal with seeing, if we just have everything diffraction limited to start with, maybe we can do better because we can constrain that very bright AGN to a much smaller region on the detector. So that's one of the benefits of attempting to go into space to do this kind of project. The other benefit you get is that space is cold and our atmosphere is warm. And in the near infrared, a warm atmosphere appears as very high sky background. So a lot of noise in your observations, whereas in space, where it's very cold and you have a nice sun shield to keep the telescope and detectors cold, you're going to have really low backgrounds by comparison. So again, we're reducing noise in this particular case to try to pull out faint absorption features from stars in the center of the galaxy. Now there's one drawback to going into space, and that's that you have to fit everything into a rocket in order to launch it, which means things tend to have to be made as small as they can be. And in that case, it means that your spectrograph may not have the spectral resolution that you might like to have or you might have available on the ground. So the one thing that we're not sure is going to help us in space is that the spectrograph has a highest resolution of about 2700. Whereas from the ground, where you can make instruments big and you can just set them in a room next to the telescope, and as long as there's enough room in there, you can make them as big as you want. You can get a resolution of about 5000, which allows you to more accurately measure the shapes of the absorption lines and therefore measure the different parameters that go into the stellar dynamical modeling. So this is our project with JWST, is to directly compare how well can we do measuring the stellar dynamical black hole mass of an AGN from space versus from the ground. We have the from the ground part completed and reanalyzed so that we've done the best we can to get ready to compare with the JWST observations. But once JWST launches, about 6 months later, we'll expect to have data coming in that will allow us to redo this project and compare the mass that we get from stellar dynamical modeling of JWST data to see how well it compares to the Gemini data I just showed you. So I've talked about a lot of different kinds of projects and I've thrown a lot of information at you, but I'll sort of just wrap it up with a few key final thoughts, which are, again, we all understand that black holes influence galaxy evolution. And as I mentioned, black hole mass is a really key property for understanding feedback and what's the feedback potential of any one particular AGN or black hole. and for measuring feedback as we see it happening in action in different galaxies nearby. But there's this concern that we have these different black hole mass measurement techniques, and are we actually weighing all black holes with the same scale, or at least a similar enough scale? If the answer turns out to be that yes, it's all fine, well, that's great, and we don't have to worry. However, it's just as likely that the answer will be that there's a problem here. And so if these two scales are not directly comparable, can we fix it? Can we figure out what the problem is and fix it relatively quickly? But if that's the case also, that might be the more interesting option, because it may actually affect our understanding of galaxy evolution and how that has progressed across the observable universe. So with that tantalizing thought, I will leave it there and I will ask for questions. So thank you for your attention. And I'll drink some water too.
Oh, thanks so much, Misty. So let's, I'll do the applause. So I think that was an excellent talk, and you have already a question in the chat. Stephanie, I think it's visible to everyone, was asking about your dynamical modeling and what codes you use. Yeah, so we started using Monica Valuri's code, MassMod, which she actually published some time ago, but has been working on. She had not made it publicly available, although had been working with several students and collaborators using it. But for this most recent project that my former student Caroline Roberts was doing, I'll just bring up the slide with her results. For that project, we're actually using a new code that Eugene Vasilev was the main writer of, and Monica Valuri was a contributor, and that is publicly available. And so it is called ForStand, I believe, is the package that includes the dynamical modeling and several other capabilities as well. And so there are a couple of papers out on the package and on some mock galaxy models and things like that. And so if you look for Vasilev and Valuri, you'll find those, and those were within just the last 2 years, I think, but that package is publicly available.
Misty, how do those codes deal with inclination? Because you had some disk galaxies and some spheroidal galaxies.
Yeah. So inclination is one of the parameters that you can adjust. And so the way that we've done this with NGC 4151 is to take, sorry, I got distracted by the chat, is to actually assume different inclinations and sort of step through them and run the set of models, and then compare those to what you think you know about the galaxy from observations, but also how well the kinematic models match your observed kinematics as well. So the case of NGC 4151, it's a bit tricky, because if you look at optical imaging of the galaxy, it looks like it's inclined at something like 40 degrees to our line of sight. But if you look at radio observations, you see that it's actually potentially much more face on, around 20 degrees, and looks quite round in radio imaging, with this very large extended gas disk that has very low stellar contribution to, so you don't see it in the optical imaging, but you really see it in the radio. So that was one of the complications for this particular galaxy, is, do we actually know what its inclination is? And that question goes back to the 70s, and they, we still are not quite sure that we know what it is. So this galaxy, I thought it was funny, so we included it in the paper. If you go back to, I think, a Simkin paper from '76, he called the galaxy pathological. I think that's appropriate for this particular galaxy. It's complicated.
So on the kind of a follow-up question. So thanks for the talk, by the way. So do you know how many dynamical components have to be used? So you don't have to model the full galaxy because the data is only a few arcsecond, but do you still have, like, is there still, for example, could they be like a small bar or some kind of double disk or any kind of more complicated components?
Yeah, so ForStand, the code that we're using, is actually the first code that will be able to model a bar. So up until now, most codes have been axisymmetric. There have been a few codes that have been able to deal with triaxial shapes, specifically when it comes to elliptical galaxies, but no one's been able to model a bar properly. NGC 4151 also has a weak bar in it. And so this galaxy we're actually focusing on in particular because we want to see how well or how the answer changes when you include the effects of a weak bar in it. So that is on the to-do list. We haven't quite gotten there yet, but this galaxy does have a bar. We are planning to model it. Forstan has that capability. We just haven't quite gotten there yet. We've been busy with other things so far.
Great, thank you.
Great. I think Anil is typing away in the chat, so he's definitely a stellar dynamical modeling expert. So Anil, do you?
I just had a question on the broadline region
yeah.
relationship. So I was just wondering about the, whether you, I know that there's more scatter now than in your original relationship now with the kind of more recent results, and I was just wondering how that impacts things on like the single epoch masses, and then whether that's calibratable or not.
Yeah, it depends on what kind of galaxy you're looking at. So if you want to call it the old version of the radius luminosity relationship, works really well for garden variety Seyferts in the relatively local universe, because you're not looking at super high accretion rate objects. And so in that case, using the old version is fine. If you start moving out to higher redshift, things get complicated because you start finding a wider variety of properties among the very luminous quasars that you're detecting, because you can't really see garden variety Seyferts at high redshift. They're too faint. And so you're limited to the most luminous objects that you can see. And so that's where we start to see more scatter coming into things. And that's because you're probing a wider range of AGN properties. So if you're working in the relatively local universe and you have a broadline AGN, you don't have to worry too much, because that's the kind of object that has been used to calibrate the, we'll call it classic radius luminosity relationship. If you're moving to higher redshift, you always have to worry. Not only do you have to worry about the fact that you might be looking at something that's not directly comparable to a Seyfert, but also you're probably not using the H beta emission line. You're probably using a rest frame ultraviolet line like carbon-4. Carbon-4 comes from a much more highly ionized region of the broadline region than H beta does, which comes from a fairly neutral region by contrast. And so you have to worry about whether or not there are differences in the kinematics of the gas in those different regions. That's a big worry that gets tossed around a lot. We don't have a good answer yet. You also have to worry about whether or not you have the signal to noise that you think you need in order to do a decent job estimating the mass. So if you're working with SDSS spectra of a redshift 3 quasar, you may only have a signal to noise of 5 around your carbon-4 emission line. Can you actually accurately measure the width of that line compared to the background noise? And the answer is, in a lot of cases, maybe not, especially if there's absorption there that you can't see because it's blended in with the noise. So yeah, high Z is complicated by a lot of factors. Higher signal to noise helps, but doesn't solve all the problems. But if you're working with fairly nearby galaxies, then you don't generally have to worry too much, because you're looking at relative, or I wouldn't say relatively simple objects, but objects that are similar to the kind that have been studied enough in detail that we think we have a decent idea of what's going on.
Do you, I guess, is it an Eddington ratio correlation there? I mean, is there some sort of Eddington ratio correlation or something? Is that what you think is going on?
It's interpreted that way by some people.
Okay.
Yeah.
Thanks.
The answer to your question is we don't know. Some people think yes, some people think maybe something else.
Great. Any other questions? Anybody? Divya?
Yeah, hi, thanks, Misty. That was a really nice talk. I was wondering, given the slew of, I guess, ALMA black hole mass measurements that's come out in recent years, I'm wondering whether or not, obviously it's probing different wavelength, different temperature gas, and they have higher resolution probably than, than the near infrared. But do you have like ALMA observations or planned or in the works for some of these galaxies, and how do you expect those to compare?
Yeah, so in fact, my colleague Mayana, I'll put her picture back up here, Mayana Vestergaard at University of Copenhagen, she is sort of taking the lead on whether or not we can use ALMA to probe some of these same galaxies. The problem in this case is that they're AGN, and so we know that the gas that's close to the black hole is heated up a lot because of the accretion onto the black hole. And so, the first step in this process was just trying to figure out whether any of these objects have cold gas in the center that we could see with ALMA. And we think we found a couple at least that will be able to do that with. NGC 3227 is one of those. And so Mayan is actually leading that particular leg of everything, but we are planning to go that direction. It's just been a little bit slower because we can't assume that we'll be able to detect anything with ALMA without doing some legwork first, and that takes a little bit of time and prep.
That makes sense. I have a follow-up question. If you can go back to NGC 6814, I think it was one of the first galaxies. So yeah, I found the velocity map really interesting, like that thing in the center, like what's going on?
Yeah, so at the center there could be, so we're talking about the velocity map, which is the leftmost one here. We're not quite sure yet. It's either that there's a little bit of residual noise from the AGN light that's been scattered out of the AO diffraction limited PSF in the center, that's sort of maybe skewing the measurements, or there could actually be a little disk that's rotating a little bit different at the very center. So that's something that we're investigating with the models as well. And so ForStand is nice and flexible and allows you to look into a lot of things. So we're gonna see if we can figure out what that is. We're not quite sure at the moment. It might be real, but then again, it might not. Also, I grabbed these maps out of an email from my student. She's on vacation right now. So I'm not sure that these are the final versions, but they were the finalist ones I could find in my email while putting this talk together.
Well, it's very interesting looking. So looking forward to seeing the results. Thanks.
Sure.
Thanks, Vivian. Anka?
Oh, you're muted, Anka.
Yes, indeed. I was just saying thanks, and so wonderful to see you, Misty, again, and everybody else. And before I get the question, if I can just say, I had my 18-year-old daughter who's kind of seeing through my colleagues specifically her future college professors around her. And she was very, very impressed. She liked your presentation a lot, and especially the initial slides where you explained everything. She's like, oh my God, I wish I had professors like her. And I said, I know, she's, a wonderful, smart, awesome astrophysicist. So yeah. So I hope you enjoyed that as well. I was just wondering, and I was kind of a wonder for a long time now, these reverberation mapping techniques. So you also mentioned in your presentation, they definitely work with Seifert ones only, right? And so I was wondering how, the instability, we know that there are the changing look AGN now. So, and we understand some things about them, but not necessarily the whole time scale in which all this variation happens. So and there are variations in how, kind of the certainty of the type 1 classification. Does that affect the results of the reverberation mapping, and how much or in what way?
Yeah, so if the broadline region basically disappears from the spectra, you wouldn't be able to see anything with reverberation mapping. You could take spectrum after spectrum, and if you don't see the broadline, it's not going to tell you anything about it. Now that you could think of lots of different ways to interpret that. Did the gas go away, or is the gas just not being lit up anymore? There are a lot of different ways you can interpret that. But we do actually have 1 or 2 objects in our sample that have gone through these changing looks. It's just that we did the reverberation mapping when they had their broadline visible. So I think, trying to remember the names of which ones off the top of my head. Markarian 590 might have been one of them. And I think there's another one in there as well. But it won't really affect the reverberation mapping. So in general, our monitoring timelines are, on the order of a couple months, which is much shorter than the dynamical time scale for any of these AGNs. And so we're not probing usually in a reverberation campaign any dynamical changes. We're probing photoionization changes, which are much faster. However, you could conceivably carry out multiple experiments, and we have done this, on the same AGN when it's in different luminosity states. And as long as you can see the broad emission line and collect enough photons from it, you could actually try to look for structural changes in the broadline region by carrying out maybe 3 or 4 campaigns over a decade, in which case you could potentially probe dynamical timescales and changes that happen on that timescale. And so that has been done in just a couple cases so far. I think ARP 151, which is one of the LAMP targets, I think that one has some results, and I don't remember what they are off the top of my head. I don't think there were any huge changes in that particular object, but you know, you might be looking at a different one. And if we actually go back to NGC 3783, which I talked about kind of a lot, you know, it's interesting to ask what we might have seen if we had done a reverberation campaign on this object about 5 years ago compared to what we saw with the data that we collected in 2020 just last year and just published, because there are some hints from X-ray observations and ultraviolet observations that maybe something really dramatic happened to the broadline region in this particular object, because it suddenly became very absorbed in the X-rays, and there were suddenly very large broad absorption lines that appeared in the ultraviolet spectrum that hadn't been there for like the previous 15 years. And trying to interpret what all of that means just from X-ray spectroscopy and from ultraviolet spectroscopy led to some potentially interesting ideas that maybe the broadline region scale height actually collapsed in this period of very low X-ray luminosity. So you just don't have enough photons to puff up the gas anymore. And if it's low flux enough for long enough, then that gas could end up collapsing on the dynamical time scale. So you know, it'd be great to get in a time machine and go back about 5 years and see what we would have gotten with a full velocity result reverberation mapping analysis of this AGN back before this period of very low X-ray luminosity happened. At this point, you know, it's possible that the broadline region has recovered, or maybe nothing that drastic ever happened to begin with. But by doing these kinds of studies over, you know, 5 to 10 year timescales in the same AGN, we can hope to maybe understand a little bit more about what kinds of changes are possible for the broadline region gas. So that's a very interesting hypothesis that I sort of touch on at the end of this particular paper that will be coming out soon. But again, it's based on a little bit of evidence and some tantalizing ideas, but not a whole lot of proof at this point.
Great. Any other questions? Can I squeeze? Oh, Gabby.
Yeah, that was a really great talk, Misty. Thank you so much. You know, the George Mason students and the UCR students have actually been getting together every week to do reviews and papers. And William, who I believe is in the audience, did a really good job reviewing measurements of black hole masses. So he covered a lot of your papers. And one of the questions that rightly so came up was, how can you make sure that the broadline region gas is actually the kinematics are gravitationally dominated. So I mentioned to them a little bit of the work that you actually, I was really glad to see that you covered the inflows and outflows. And but you know, I just barely mentioned it to them. And I was wondering if you could tell us a little more about what all we've learned from doing the kind of modeling that you were showing us.
Yeah, so the first hints that, you know, we could probably rely on the masses as being coming from gas that's dominated by the gravity of the black hole is actually looking at different emission lines in the same AGN and looking at the time delay that we get relative to the velocity width of those emission lines. And so if the gas is gravitationally dominated and you're just sort of looking at different layers of the onion based on ionization state of the gas, then you would expect that the time delay goes as the line width to the -1/2 power. And so we were able to do that in a few AGNs. You know, in a lot of cases, it's required ground-based monitoring to get the optical emission lines at the same time as ultraviolet monitoring from space to get the higher ionization emission lines. And some of that work was done in the early days of reverberation mapping. And so that's where a lot of the initial foundation for believing these masses are most likely in the right ballpark came from. But with going into the modeling, we actually have more evidence now. So if we can actually use all of the information that's in the reverberation mapping data, we can actually look at the time delay as a function of velocity, and then that maps into position and Doppler shift of the gas. We can actually figure out what the kinematics of the gas are. So in NGC 3783, which I have up on the screen again here, not only did we find that the broadline region is well described by a thick disk, but the kinematics of the gas in that disk are dominated by rotation with a significant component of inflow. Well, inflow is also going to be gravitationally dominated because the gravity is pulling the gas in. And so those two things are telling you that at least for the H beta emission line, the kinematics are dominated by gravity. Now, the helium-2 emission line at 4686 was an interesting difference. So we found, we looked at both for this paper, and we found, as expected, that the size of the broadline region for the helium-2 emission line was much smaller. So it was a time delay of about two days. And so the size for the helium-2 broadline region is sort of the inner hole that you see here for the H beta broadline region. So it's much, much closer to the center. But we also found that the kinematics were potentially different for the helium-2 emission line, which preferred an outflow kinematic, which may not be surprising considering that the gas is significantly closer to the AGN. It's much more highly photoionized, and it would be expected to be coming from gas that's lower density, and would therefore, all of those things combined would make it more susceptible to radiation pressure that could be blowing it out. Now, outflow doesn't necessarily mean non-gravitationally dominated, because it could mean that the gas is going out on elliptical orbits and falling back in eventually. It may not be completely escaped. And so that is something that's included in the modeling, or at least this kind of modeling for reverberation data. In this case, we found that the mass that you get from modeling either of those emission lines is in agreement. So you see the plot on the bottom right, that blue curve is showing you the range of masses that are constrained by the H beta modeling. So this more neutral gas where rotation and inflow are preferred. And then the red line is showing you the helium-2 range of black hole masses, and that's with outflow dominating. And the joint analysis between the two is really heavily weighted by the H beta emission line, which is higher signal to noise. It's just it carries a lot of the weight because it has better characteristics for modeling. So it's a brighter emission line. We were able to get higher signal to noise on it and control the noise characteristics better than the helium-2 emission line, which is really low amplitude in the spectra, and therefore a lot more noisy. But even so, the masses agree fairly well, and the joint constraint gives us the final mass that we adopted. So we use the results of both. So in this case, even if outflow is what's actually happening with the helium-2 gas, it's still giving us a mass based on the gravitational influence on those outflowing orbits that's in agreement with what we would get from gas that is rotation and inflow dominated. So at this point, most studies of AGN, there's about 12 of them now at this point that have been modeled in this kind of way. Almost all of them are finding really similar things. H beta in particular, which is the main emission line that we use for reverberation mapping, is almost always appears to be arranged in a thick disk, inclined at some moderate angle to our line of sight, almost always rotation dominated, sometimes with a large component of inflow. And there are very few exceptions to that among the objects that we've looked at. That's only 12 so far, but this is kind of a hard thing to do, and it's encouraging that we're finding similarity from object to object. One thing that's different though from object to object is the inclination, as you would expect. We're not getting the same inclination for all AGNs. They're all closer to face on than edge on, like you would expect for a CFERT 1, for a broad line AGN, but they're not all the same. And as long as that inclination angle is within about 20 to 40 degrees from our line of sight, the black hole mass that you get generally agrees quite well with what you would assume from the very simple estimate where you have to include an F factor. It's just the few AGN where we see the inclination is more like 10 degrees to the line of sight, it's getting very, very face on, that we start to see more meaningful differences between our simple estimate of the reverberation mass and what we get when we do the full dynamical modeling. And again, that's just because the component of the velocity that you're seeing is so small compared to the total velocity. So that was a lot of information. I hope that answered the question well.
Oh, very much so. It was very interesting. Thank you. And if I may ask a follow-up question, since you mentioned the helium-2 with the lower density and higher ionization, it just made me think about how you've been coming to the talks. There's been a lot of talk about coronal lines, and I'm wondering if anyone has ever looked at any coronal lines in reverberation mapping studies.
No, the closest that we've gotten to that is looking at some absorption lines in the ultraviolet. So there was an HST and joint ground campaign monitoring NGC 5548 a couple of years ago, and we've now written something like 20 papers on this one object and this one campaign because of the huge amount of data that we've collected. We were able to actually detect some changes in a few of the narrow absorption lines and figure out approximately where they would be with respect to the broadline region, but I don't know that anybody has looked at coronal lines at this point. So that's, I think that is one of the few things that nobody's attempted or maybe someone attempted and didn't publish, I don't know, but I don't think I've seen any papers about that.
Great, thank you. Maybe this is something for this group to do.
Or at least consider. I haven't thought about it, and so I wonder how that would work. We did actually, I will also say we have seen, you have to wait a really long time, but we did see a time delay in the narrow oxygen 3 emission in NGC 5548, and that was only able to be measured with multiple campaigns, something like 12 campaigns over the span of 15 years. And each one of those campaigns is 3 to 4 months in length with spectra taken almost every night. So that's a huge investment of resources. But if you have a lot of telescope time and some patience, we could probably do that for some other AGN as well.
Great. So Gabby, you asked my question, which is good because I didn't want to keep people, but I have like maybe an informal question, Misty, if you have time later.
Yeah.
And a smaller group if anyone wants to hang out to just talk about diagnostic potential with JWST and future facilities. But I wanted to thank you for that excellent talk. And again, as Gabby said, your review articles and the references that you provided for black hole mass measurements were really valuable to our group. And these summer sessions have been really nice. And I wanted to say actually here that we were thinking about having like a student session as part of this seminar series, like maybe we could pick a date and anyone who's interested could have their students join and we can have a smaller network of student discussions, maybe talking about their research projects. So email us if you're interested in something like that.